welcome everyone, and today we are happy to have Mokhtar Hassaine, and he will speak about the role of symmetry for finding black holes in scalar-tensor theories. So please, you are welcome to start.
Okay, thanks a lot. First of all, I would like to thank the organizer, in particular Dimitri, for inviting me, for giving the opportunity to talk about some of my work, the recent work that I've been done. Today, I would like to talk about the role played by symmetry, in particular the conformal symmetry for finding black hole in what is called the scalar-tensor theory. By scalar-tensor theory, I mean gravity theory with a scalar field, a dynamical scalar field. Okay, I will precise all the notion in the talk. So my talk is going to be divided in 5 parts. In the first part, I will present what is known as the scalar-tensor theory. Okay, I will present the most general scalar-tensor theory that yields to second-order field equation for the scalar field as well as for the metric tensor, and this is now known as the Horndeski theory. Then after, in the second part, I will give an historical overview of solution of scalar-tensor theory for which the symmetry has been proved to be of great help to find analytic solution, explicit solution, to say it in other words. In the third part, I will present a model that has the advantage of having the field equation implies a certain geometric constraint, but the scalar field the scalar field action is not conformally invariant. Okay, I will explain the construction of this model, and as I will present also the solution. In the fourth part, I will present a model that belongs also to this Horndeski theory that has a very simple scalar field equation. I will present the construction of the model and present the solution that has very nice solution that I would like to talk about. This is the work that I've been done with my collaborator, Yevgeny Babichev, Christos Charmoussis, and Nicolas Lecoeur. And then in the last part, I will conclude and give some further prospect. Okay, as everybody knows, scalar-tensor can be guessed as one of the simplest modified gravity theory, which extend the general relativity with one or more scalar degrees of freedom. In our case, we are going to consider only one scalar degrees of freedoms. And in the 70s, it was shown by Horndeski that the most general single scalar tensor theory that yields to second-order field equation for the scalar field as well as for the metric tensor, which ensure the absence of Ostrogradskis ghost, is given by a linear combination of these 4 Lagrangian that are given by K, determined by K, G3, G4, and G5, that are arbitrary function of the scalar field, this kinetic term. And in this expression, G4x or G5x, it's nothing but the derivative of G with respect to x. So this is completely undeterminate function. But with that, with this linear combination of all these Lagrangian, we ensure that this is the most general that yields to second-order field equation, and is known as Horndeski theory. And the main goal is to find static and spherically symmetric black hole solution of this kind of theory that belongs to the Horndeski theory within an ansatz of this form. I mean, in the Schwarzschild coordinate that a priori we have 2 metric functions with a scalar field that only depends on the radial coordinate, or sometimes it's much more advantageous to work with what is known as isotropic coordinate. Is completely equivalent, and they are diffeomorphic, but sometimes it's much more simple to work with the isotropic coordinate that's also defined by 2 metric function, and the scalar field we are always going to consider a scalar field that only depends on the radial coordinate. And as everybody knows, we know that the Einstein equation, the non-linearity, make difficult to find exact analytic solution. So we are going to see when symmetry can help to find explicit solution. But first, I would like to see for sure.
So one thing is that so there are also these theories called the host, right? Are these not real, or you know, DHOST?
Yeah, but they are beyond this theory. They have no, they are not covered by this Horndeski.
But they're unhealthy, or what's wrong with them?
Yeah, they are healthy, but I'm just considering in this case Horndeski theory. Of course, I can consider those that they are healthy in the sense that they are not propagating stroboscopic ghost. But I'm not considering this case in here.
Okay.
But of course, yeah, of course, there is this what is non-degenerate higher order that's are beyond the Horndeski theory. Yeah.
And can you also show your ansatz for this spherically
Yeah,
symmetric?
for sure.
Why do you have like two independent functions, not three? It seems that you can put also another independent function in front of this bracket.
Yeah, but you can always redefine the radial coordinate and to put it like R. This is the most general. Huh? If I have here a function, I can define this as my new R variable, and then I can end up with this kind of metric. This is the most general.
Okay, thank you.
No, you're welcome. Please feel free to ask whatever you want. If I can answer, it will be very nice. Okay. So the first simple case that I'm going to consider is Einstein gravity coupled to a massless scalar field. In this case, it's very simple. It's Einstein gravity plus the standard kinetic term. This corresponds to Horndeski with J4 is equal to 1 and K is X. This is the kinetic term. And the most general static solution has been found a long time ago by Tsantopoulos and Sanias. And the solution was precisely found in the isotropic coordinate, okay, because it's very useful in this case to use this isotropic coordinate, and the solution present naked singularity, unless of course if the scalar field vanishes, and then we end up with Schwarzschild, of course. But you know, this result, it was not a surprise because it was already covered by the Noether theorem done by this mathematician Chas. That he was already know that it was already know that the solution will not correspond to black hole. But then with this, we have an explicit solution, and we can see that effectively there are naked singularity. And the clue of the derivation of this solution is that the scalar field equations is given by box phi the Laplacian of phi is 0, and that gives a first integral for phi, and that's help a lot in order to find the solution. This is the clue of the derivation, this equation. Then we can raise a bit the difficulty and still consider Einstein-Hilbert, the standard kinetic term for the scalar field, a possible self-interacting potential, and then we are going to consider a nominal coupling between the scalar curvature and the scalar field. Okay, and this xi, this parameter, is a constant that precisely measures the strength of the non-minimal gravitational coupling. Okay, when xi is 0, we are in the minimal case. Okay, so of course this theory also belongs to Horndeski theory with k given by x minus v minus the potential, and G4 is given by 1 minus xi over 2 times p squared. In the minimal case, I mean, when we do not have the non-minimal coupling between gravity and the scalar field, and for increasing potential, Bekenstein has proved a no scalar theorem. Okay, it was already known in this case. And later on, it was extended by Mayo and Bekenstein that for xi, for the non-minimal coupling non-zero, for xi negative, or xi greater than 1/2, there is also, and for a definite positive potential, there is a no scalar theorem also shown by Mayo and Bekenstein. But in between, you know, there is the Noether theorem is not covered, and precisely there is a solution. There exists a solution for the coupling 1/6. Okay, and for potential V, in the case of the absence of self-interacting potential, this was been shown by Bochorava, Bronikov, and Melkinov, that they found a solution in the 70s, and it was published in Moscow State University Bulletin. Okay, and this result was not known from the West because of the Cold War. And 4 years after, Bekenstein rediscovered this solution, and now is known like the BBMB. Okay, with the initial of each of the guys that they found it. So the solution is given by this metric, and the scalar field has this expression. Okay. One can see that the metric is like the extremal Reichern nostrum. Okay, even if there is no electric charge, but it resembles like extremal Reichern nostrum. The horizon is localized at m. M is the integration constant that corresponds to the mass. Okay, and there is something that is maybe pathologic, is that the scalar field blows up at the horizon. Okay, R, when R approaches to m, this blows up. Okay. There is a uniqueness theorem for this solution that has been shown by Xantopoulos and Sanias in the 70. And when we can say that the BBMB has a very, very scanty hair that is due to this dichotomic parameter that is mainly due because of the theory is invariant under the discrete symmetry phi goes to minus phi. Of course, if I change phi by minus phi, these two terms are invariant. Of course, the potential is not present. So this discrete symmetry is present. And this is what they say that there is a hair for this solution. Okay. The clue of the derivation and of the uniqueness theorem of the BBMB is exactly the conformal invariance of the matter source action. By matter source action, I mean that
can I ask, is there also another solution, phi equals to 0 and Schwarzschild?
Yeah, of course, yeah.
So
yeah.
black hole is kind of not unique in this case.
Sorry?
The black hole is not unique in this case.
Yeah, of course. It's up to, of course. Yeah. So, sorry, of course, yeah. You can recover Schwarzschild. I agree with you. But I was thinking for a non-trivial scalar field.
Okay.
But should there be an independent charge for the scalar field?
Yeah. You sorry?
Should there be like independent integration constant here?
No.
No.
The only integration constant is the mass.
And why is it better than? Well, I'm not an expert, but I saw that the reason why one has these no-hair theorems is precisely because there are some issues like stress energy tensor blows up at the horizon, and that's why people rule out them, right? And here you have a solution which is also singular at the horizon.
Yeah, but it's only the scalar field, huh? you know. But it's, to be honest, here in between these two values, you do not have any. You cannot use this theorem. This is really specific for this range of C. Okay, but I will show you another solution where the scalar field is not blowing up, and you know, it's not. It's also for C equal 1/6. So it's not because of that.
Okay, thank you.
No, you're welcome. So as I was saying, the clue of the derivation of the uniqueness theorem up to Schwarzschild, thanks for recalling me that, is that the matter action, I mean the pure matter action, is conformally invariant. What I mean by conformally invariant is mean that if I consider an arbitrary conformal transformation of the metric, sigma is an arbitrary function, and I rescale phi in this way, with this same metric function, but with a different weight, this action maps into itself up to boundary term. So it's a truly symmetry of the action. And in this case, because of the conformal invariance of the matter source action, when I take the trace of the stress tensor, it vanishes. Okay, so the trace of T mu is 0. And then after, from the Einstein equation, of course, if I take the trace in both sides, I will get that the curvature is 0. I get my pure geometric constraint. Okay, any solution must have R equals 0. And on the other hand, the scalar field equation is box phi is 1/6 R phi. But since R is 0, the scalar curvature is 0, I got box phi is 0, and then I got a first integral for the scalar field. These two ingredients permit the derivation of the most general static spherically solution, which is nothing but the BBMB solution, because really it's using this constraint and this first integral that allow you to derive the most general solution. Okay? And this was done by Xantopoulos and Sanias. Okay, so this same game.
Can you just gauge away phi to 1 and solve just pure gravity equations of motion?
You mean if I go to phi equal to 1?
Yeah, using this conformal transformations, you can set phi to 1, I would say.
Yeah,
right?
yeah, for sure. Yeah. And then I should recover either a flat or Schwarzschild. Yeah.
Okay.
Yeah, for sure. Actually, you know that Bekenstein, when he derived his solution, he used this trick. He made the conformal transformation to generate the black hole. It was exactly what he did, Bekenstein. So you can go to higher dimension, okay, and to ask the same future for the matter action, okay. You can do it, but the price to be paid is to change this non-minimal coupling is given by this expression, okay. Of course, it is depending on the dimension, and of course, the weight of the scalar field is also changing because of the dimension. And then you can see that also this action is conformally invariant under this full transformation. The action maps into itself up to boundary term. And we can make exactly the same game, okay? Taking the trace of the Einstein equations, you get the scalar curvature is 0. And then from the scalar field equation, you get that box P is 0, you get the first integral. And then this is what has been done by Klimschitz, that is derived most general static spherically symmetric asymptotically flat solution. And it was very nice result because he was able to show that the solution describes a black hole only in the equal form. And it corresponds, of course, to the BBMB solution. It was the only dimension where this theory will describe a black hole is in 4D. And it was, of course, the BBMB solution. So since the conformal invariance is playing a very interesting role, and it's helping a lot in the derivation or in the establishment of uniqueness theorem, you know, a simple way to keep the conformal invariance is to add a self-interacting potential that is phi to the 4 with some coupling. Okay, and in this case, all this part is conformal invariant. It's not this potential does not break the conformal invariance. Okay, this is actually is the unique potential that is compatible with the conformal invariance in 4 dimensions. And in this case, one can show that there is a black hole solution provided to introduce at the same time a cosmological constant that has to be positive. That has been done by Chilean collaborator, Martinez, Troncoso, and Zanelli, and the metric is given by that. And you can see that in order to ensure to have an horizon, lambda must be positive. Okay, but what is nice for this solution, for answering to one of your questions, is that now the horizon, it's not at r equal m. So this singularity that the blow-ups of the solution is not, it's inside the horizon. Okay, so the scalar field blows inside the horizon. So it has no consequences because this happened inside the horizon. And this is the product of turning on the cosmological constant. Of course, this solution exists only if alpha and lambda are tied by this relation. Okay, and for sure, when lambda is 0, we recover the BBMB solution. Okay, alpha must be 0, and we end up with the solution that I showed you previously. But in this case, yeah, you can always, of course, the trace of Teminu is again 0, so you have now this constant that the scalar curvature is proportional to the cosmological constant. But in this case, because R is non-zero and we have this self-interacting potential, we do not have box phi equals 0. So you do not have a first integral. And hence, the uniqueness of this solution is still an open problem. We cannot say, as in the BBMB case, to establish that this is the unique solution. It's at least not with the technique that has been used in the case of BBMB. But anyway, from this different example, one can appreciate that the solution that I have presented to you can be found practically in the case where there was a pure geometric constraint, that it was due essentially to the conformal invariance of the scalar field action. And this, in general, of course, restricts the allowed possible space-time. Of course, if I have R equal 4 lambda, this is going to restrict me the form of the solution of the metric. Okay. And also, that's why I put or and when the scalar field equation is simple between quotes to integrate, like in the massless case that we have box phi equals 0, and this provides us a first integral that it was very useful in order to derive the solution. So in what follow, I will present to you a model where these two criteria hold, but the action is not conformal, the scalar field action is not conformally invariant, but we still have a pure geometric constraint. Okay, so let me first present the model, and then I will explain why these terms occur. So I still consider Einstein-Hilbert plus a cosmological constant. Here we have the conformally invariant action that is in magenta with the conformal potential that is, and then I'm adding this term in red that involve the Gauss-Bonnet, the Einstein tensor, and these two terms with very precise coefficients. So G is the Gauss-Bonnet density. We know that the Gauss-Bonnet density is a boundary term in 4 dimensions, but now is multiplied by some functions of phi, so it's not longer a boundary term. So it's contributed to the field equation. This theory belongs to the Horndeski theory, so you can specify explicitly. I'm not going to do it, but you can specify what are the coupling functions that I present in the very beginning of my presentation. And when you can show that, when you can see is that the alpha contribution, this piece explicitly breaks the conformal invariance of this magenta part. We know, I have shown that this magenta part, it was conformally invariant, but now this piece breaks the conformal invariance. But I will explain later, but even if the action is not conformally invariant, I mean the scalar field action is not conformally action, the scalar field equation is conformally invariant. I mean the variation of this action with respect to phi is conformally invariant. And this is going to help in order to find solution. So the idea is to look for a simple ansatz. Now I'm not only considering one metric function because otherwise it seems to be impossible to integrate the system. But since we have a pure geometric constant, now it's given by R minus 4 lambda, as it was the case in the conformally case, but now we have plus this contribution of the Gauss-Bonnet is equal to 0. This is a quadratic equation. That's why we have a square root that appear, okay, because of G is quadratic in the curvature, okay? So when you solve this constraint for this specific ansatz, okay, it's very simple because you end up with a second order equation. Okay, of course, you have two branches. One is it has a GR limit and the other has not the GR limit. Since it's a second order field equation, you have a priori two integration constant. M is the mass and Q is a kind of charge that is going to be fixed by the remaining integration, by the remaining Einstein equation. And what is nice for this case is that the scalar field equation is very simple to integrate. Okay, you have these two branches. You have this first branch and this second branch. Okay, so you can see that this model. Then after I will explain how to construct this model. Yields to a very simple expression for the metric function as well as for the scalar field. We have two branches of solution. Either this is 0 or this is 0. And this was done by Fernandez very recently that has considered this model. So the first branch, I mean the red one, happened for lambda. Lambda is the coupling of the potential of the conformal potential. There are this at this special point, lambda is beta squared over 4 alpha. This charge is fixed in terms of the coupling potential of the Gauss-Bonnet piece, okay, of this alpha piece. Okay, and the scalar field is like dilaton scalar field is 1 over r, or if you go to the other coordinate, it can be an exponential if you want. The second branch is very nice because it can be integrated by means of this. If you change r phi by this integral, by an arbitrary function of this integral, then this equation becomes separable. And then you get an explicit solution given in terms of this integral. And what is very nice is that we have the solution is characterized by an integration constant that is a sort of hair because it's not related to any Gauss law. And this is a direct consequences of the fact that the scalar field equation is conformally invariant and not the action. I insist on that. It's only that the scalar field equation that is conformally invariant. Now I will explain why the clue behind the existence of this solution. And so, as I said, the geometric constraint, this one that I was considering, is due to the conformal symmetry of the scalar field equation, and the action is not conformally invariant. This is what is called generalized or non-Noetherian conformal scalar field. Non-Noetherian because it has not a Noetherian origin. Okay, it's not related to the invariance of the action, but rather to the invariance of the scalar field. And it's very simple to understand how it works. Just for simplicity, we go to the exponential frame or to the dilaton frame. I change phi by exponential phi. It's very useful to use this frame just because of simplicity. Now the conformal transformation. The conformal transformation, it becomes a translation because now I'm using the exponential. Okay, so it's just a translation of phi, or in infinitesimally, it means that delta sigma of the metric is proportional to 2 sigma g mu nu, and delta sigma of phi is minus sigma. Okay, that can be seen from there in the infinitesimally. So if I take the variation of the action with respect to this sigma, with this infinitesimal parameter sigma, I got this stress tensor and the equation for the scalar field. Okay, when I plug these things, if I can show that this quantity is phi independent, this is what ensures me that the scalar theory, the scalar theory is conformal as a conformally invariant scalar field equation. This quantity must be phi independent. Okay, to ensure me that the action, that the equation of motion will be conformally invariant, not the action, only the equation. So if the scalar field equation is conformally invariant, we have this quantity that is like the trace of the T mu nu plus the equation of motion with respect to phi is a pure geometric constraint. And it was exactly what I got here. Okay. And one can see also if I have a scalar quantity, I'm not talking about action. I'm just considering a scalar quantity, how is going to change under a conformal transformation. Okay, so I say to you, yeah, the conformal transformation, now I'm in the exponential frame, it's like, yeah, considering this conformal factor for the metric and this translation for phi. So if I have a quantity, it's going to change like that. Now, if I'm asking that this quantity is conformally invariant, it means that these two quantities must be equal. These two quantities must be equal if this quantity is conformally invariant for any sigma. Okay, for any sigma, of course. In particular, for sigma equal phi, and in this case, we can see that if I choose sigma phi, any conformal quantity can be described in terms of this auxiliary metric. I mean, this means that if you have a conformal scalar quantity that is conformally invariant, it means that you must be able to write it like some things that depend only on this auxiliary metric. And this is very simple to understand because of the form of the auxiliary metric. The auxiliary metric is invariant under this transformation. If you see, phi is going to phi minus sigma, and g is going to exponential to sigma. So the contribution of sigma of delta j tilde is going to be 0. So any quantities that you are going to construct out of this auxiliary metric is going to be invariant, conformally invariant by construction. Okay. So the conclusion that the only conformally invariant quantity of scalar-tensor theory are purely geometric quantity that they are built of this auxiliary metric. And in our case, the quantity that we are considering, because of the Lovelock theorem that to ensure me that the equations are going to be of second order, I mean, is a constant, the scalar curvature, and the Gauss-Bonnet. These are the three densities that I can consider by the Lovelock theorem that guarantee me to have something that is conformally of second order. And then from this, by a nomotopy calculation, this is going to yield to the conformal potential, this to this conformally action of the scalar field, which is non-minimally coupled. And this part, this magenta part, is the extra part. Okay. And
excuse me, can I ask? I large is an action, right? In terms of G tilde.
So sorry, can you repeat?
In the first line, you have I large. Is this a Lagrangian or a theory with G tilde?
No, this G tilde. One, you are talking about this G tilde.
No, I'm talking about I large in the left-hand side. In the left-hand side, you have is this the Lagrangian?
No, it's a scalar quantity.
Yeah,
it's actually is the yeah, very good question. This is the equation when you vary this action with respect to phi. This is going to give you this, exactly this. But for the you see, all these quantities depend explicitly on phi. So this is the scalar field equation, exactly the scalar field equation that arises from the variation of this action.
Okay.
This is the scalar field equation. It's a very good point. Yeah. This is when I vary this with respect to phi, this is the equation that I get. This equal to 0. But written in a very compact way. Okay. What I'm doing is the inverse part. I'm starting from the equation and then constructing the action. Okay, this is the action, the action that is conformally invariant. Okay, because this is conformally invariant, this is conformally invariant, of course, this is conformally invariant, and then I'm constructing what is the action that gives me this as a consequences of the variation with respect to the scalar field. Okay, that's why I was telling that if you want to ensure something of second order for the metric and the scalar field, by the Lovelock theorem, we know that the only quantities must be a constant, a scalar curvature, or the Gauss-Bonnet. Okay, but in the action, in the equation. Okay, then after we have to construct the principle of action that gives rise to these things. And it's okay?
Yes, thank you.
Okay, you're welcome. But precisely, it was something that I have been done recently with one of my collaborators of Mexico. That a priori we can construct whatever of quantities like that, but the real challenge is to determine these scalar quantities that are built off the auxiliary metric, but that they come from an action principle. Okay, and this has to do with we have done this recently in this paper. We have determined the most general action in 4 dimensions that gives a non-Noetherian conformal scalar field action satisfying a second order equation, but only for the scalar field, not for the metric, because here we consider also Weil, and Weil is of higher order. Okay, but it's just to mention this last work that I did. Okay, so now what was nice with this model is that we have a pure geometric constraint that it was very useful to find a solution, at least to find the metric solution, but also we have this factorization of the scalar field that it allows to find the expression of the scalar field. So it's very useful when you have to solve a scalar-tensor theory, because you have to find the metric and the scalar field. So we started from this observation, and we were asking if we can generalize this model in order. We know that this model is the most general that will get this geometric constraint. We cannot have more than this pure geometric constraint. So what we decided to do is to find how to extend this model in order to still have a certain factorization of the scalar field equation that allows us to find the form of the scalar field. And then after to see how to get the metric. Okay. And this is what we were doing with Yevgeny Batvichev, Christos Charmoussis, and Nicolas Lecoeur. So a priori, we decided to forget about symmetry, about conformal, shift, and whatever you want, and ask that similar factorization for the scalar field equation will yield. I mean, we start with an ansatz like that, and we would like to see if we can generalize this action in order to get a similar factorization for the scalar field. As I said, we have to forget about conformal and things like that because we know that the previous action was the most general. So what we decided to do is to consider most general potential in the action, okay, that the one that it was considered in the previous case, you know, in the previous case, W was given by that, before by that, so we consider most general function of phi, okay, and the main point is to consider this combination of the Einstein equation, ETT minus ERR, okay, because with an ansatz like that, we managed to have this kind of factorization. We have these two branches, as it was the case for the previous model that I showed to you. And this factorization was possible provided that the potential V4 and Pi, all these potential, V4, V4, V2, V3, V4, can be parameterized in terms of the Einstein and Gauss-Bonnet potential. I mean, in terms of this potential and the Einstein potential and the Gauss-Bonnet, and this one, okay? I mean, this one, this VK, V2, V3, V4 are parameterized in terms of W and V. Z is not appearing because we are considering an ansatz of the form F and 1 over F. And when we make this difference, the terms that are proportional to V disappear. Okay? So a priori, we have a free parametric class of possible integrable theory. They are parameterized by W, the Einstein-Hilbert potential, the Gauss-Bonnet potential, and this potential term that I just mentioned to you that is insensitive to this difference. And so the next step is to fix the potential, this free potential. So here, when we consider this linear combination of this equation, we have solved one of the equation. So the challenge is to fix this potential such that the two remaining independent Einstein equation admit the same metric function. Okay, so we decided we take this first branch for phi and we inject it. For the first branch, it remains to us to solve two independent equations, epsilon RR and epsilon theta equals 0. These are the equation, the Einstein equation. And one can see that for the first branch, I'm considering this branch, epsilon RR can be integrated once and epsilon theta twice. They have this expression, E1 and E2. We are redefining these things just for simplicity. And you see, we have two quadratic equations that define, of course, F. F is given by a quadratic equation. And we know that if we want to have the same solution, these two equations must be proportional, okay, to define the same metric function, the same quadratic equation, okay? And so what we require that this E1 is proportional to E2 with a factor 2 mu of R. A priori, the factor can be any function of R. And this will ensure us to find what will be the potential V and W and Z that ensure that we end up with the same metric function for both. Okay. So the first case that we have considered is the case where this factor of proportionality is equal to 1. Okay, for a proportionality factor mu is equal to 1. So when we integrate the form of the potential, we get that W has this form, Z has this form, and V has this form. This was the Einstein potential, this was the Gauss-Bonnet potential, and this was the potential term. And it was it's very funny because we never mentioned any symmetry, but then the resulting action, of course, in red is the one of Fernandez. It's the conformal one that I show you, that the non-Noetherian conformal action. I mean non-Noetherian because of this alpha 4 piece. But in magenta, it was very surprising for us that the order that has subscribed 5 is exactly the density that is conformally invariant in 5 dimensions. So even if we do not require any conformal invariance, the resulting action is a linear combination of something that yields to a conformal equation in 4 plus something that defines a density that is conformally invariant in 5 dimensions. So it's very amazing that this occurs. Yeah, once we have done that, we have fixed the theory. I'm going to use the Eddington-Finkelstein coordinate for later convenience. I'm comparing that. It's exactly equivalent to that in this case. It's completely equivalent to this ansatz. I'm just, because then after I would like to present some other solution. Okay. So U is the retarded or advanced time, and K is the curvature of the Base manifold. It can be 1 if it's a sphere, -1 if it's an hyperbolide, and kappa is 0 if it's a plane. Okay, it's more general Base manifold of constant curvature that you can consider in 2 dimensions by the Gauss theorem. And I take phi to be a log of eta over r because it's the solution of this branch. Okay, and eta a priori is a constant. Now, because I choose to the Eddington-Finkelstein coordinate, the invariant, the remaining equation are AUU and E theta theta. So when I plug it to AUU, you remember that it was a first derivative. When you integrate this, I have a constant of integration that is for me. Epsilon theta theta, it was a second order derivative. When I do that, I get this with 2 integration constant, C2 and C3, because I have a double derivative. So a priori, C1, C2, and C3 are 3 integration constant. So this defines to me 2 quadratic equations for F, if you can see. Okay, of course, depending on the coupling of the theory and of the constant of integration. And now it's very simple because I have 2 quadratic equations. I will require that they are exactly equal. So I have to, as you can see, the red color has to be with the red color, the blue with the blue, because I'm with f over r. This part is f over r squared. That has to be equal to this part, etc., etc. And this is going to fix me the compatibility relation between the coupling of the theory, because I still have a lot of coupling. I have, you remember that the theory was determined by beta 4, beta 5, lambda 4, lambda 5, alpha 4, alpha 5. Okay, to ensure me that this is the same solution, I have this compatibility relation between the coupling constant and, of course, also between the integration constant. In fact, this and this C1 and C2 are nothing but the mass, okay, or minus 2m. And the remaining integration constant is related to the curvature of the base manifold of kappa. And in fact, the only integration constant that remains, it's the mass, m. Okay, and then we obtain this family of solutions that they are parametrized by alpha, eta, alpha 4, alpha 4, alpha 5, and eta. And it has a unique integration constant that is the mass of the black. The solution, of course, when kappa is 1, it has a standard fall-off, okay? It has a Newtonian fall-off if you make an expansion around infinity, okay? But this is for the case mu equal 1. Yeah, there is a very particular case for this solution that I would like to mention. Sorry. When the curvature is 0 of the Base manifold, when I'm considering a planar Base manifold, you see, kappa is 0, so beta 5 is 0, beta 4 is 0, lambda 5 is 0, and lambda 4 is 0. So I just end up with, when kappa is 0, the theory is restricted to lambda 4 is equal to beta 4 is equal to lambda 5 to beta 5 to 0. So I'm just ending up with the Gauss-Bonnet pieces of the action, okay? Either this non-Noetherian piece or this that is conformally invariant in 5 dimensions. And in this case, it's very interesting because the solution is given, it's only parameterized by alpha 4, m is an integration constant, and eta is also a free integration constant. It's like a hair. But it can be explained why the solution does not depend on alpha 5. It turns that for this solution, the T mu, the stress tensor associated to this piece, vanishes identically. For any value, of course, it's insensitive to alpha 5 because all the piece that depends on alpha 5 for this solution vanishes. This is what in the literature is called a state. Okay, and also you can explain why this solution has a free integration constant for the mass for the scalar field. This eta does not appear in the metric. Okay, it's not appearing in the metric, and it's very simple because, as I say, the alpha 5 it's completely on the on shell. It's going to be 0, and if you see when phi, I make a shift of phi goes to phi plus constant. Of course, this part are invariant, this part are invariant, this part invariant. But this is going to give me phi Gauss-Bonnet plus constant of Gauss-Bonnet. But we know that Gauss-Bonnet alone is a boundary term. So this is a symmetry of this alpha 4 part of the action. And that's why we have this freedom of this constant that appear in the solution, but only for the planar case. Okay. There is also another solution that is very nice. Is in the case when beta 4, lambda 4, and alpha 4 is equal to 0, and I make a redefinition from the exponential to the phi frame just for and then we have this theory, and in this case we have a linear solution, not a quadratic. I mean, you see, the alpha 4, it was the things that make me that impose me that is a quadratic equation. When alpha 4 is 0, I end up with a linear equation for f, and it's very nice because it corresponds to a solution with a non-minimal coupling that is 3/16. It was exactly, if you remember in the very beginning of my talk, I was mentioning this Noether theorem of Mayoux and Bekenstein, that it was in this range, that it was not known if there is more solution than the BBNB. Of course, we are out of the hypothesis of the theorem because we have this alpha 5 piece that it was not considered in the original Noether theorem, but this is not contradictory with this Noether theorem of Bekenstein because it's exactly inside the allowed part of the range of C where the possibly black hole may exist. There is also another solution that I would like to explain to you, that for these two branches, either the linear or the quadratic, this one is, let's call it the quadratic, and this one the linear, okay? We can go from the static solution to Weidian-like solution. And it's very nice how to do that. So you can allow the metric function to depend on, as well as on the retarded time or the advanced time. It depends here. You can have a plus also. Okay, but I will allow the metric function to depend as well as on the advanced time or retarded time. Okay, eta is the same that it was considered by it was fixed by the compatibility condition that ensure me that one of the equations is satisfied. When you do that and you reproduce exactly the same computation that I showed to you, it's very nice that for this theory, you see you remember that the two remaining equation was epsilon UU and epsilon theta theta. When you do that, the dependence on U, you see this derivative of U is exactly the same piece that something is missing here. Okay, but it's exactly the same piece. You see alpha 4 F squared, blah, 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 F, and all this extra piece only depend on R. So I can add it here. So I can rewrite this equation like dr minus 1 over F du of this density that correspond to the previous density, exactly the same, but now evaluated in F that depends also on the retarded time. The same happened for the epsilon theta theta equation, that we get that. And this is very simple to integrate. So I have two integration function now. It's exactly the same game than before. But now, since I have two coordinate U and R, it's not constant that appear here, but they are function of the retarded time. So I have this. So when I plug this in the epsilon UU equation, I get that expression. It's very simple because it's just to make this derivative of that. And you see, if I choose this integration function C1 to be 0, I end up with exactly something that is like Weidia relation. I have the difference of the Einstein equation minus the stress tensor is proportional to the time derivative of the mass. And so what it's telling to me is that the compatibility condition that I have shown to you, they always can be accommodated to a time dependence. And this can be done just by promoting the constant mass to a function of the retarded or advanced time, as I did that. And this automatically is going to be a solution of a Weidia type. It is going to be promoted to a Weidia type solution. Okay, and this, it's, for example, for the BBMB solution, this is not true. It's just for this kind of term. Now, I just consider the case mu equal 1, but let me now define this density that are conformally invariant in, this one is in any dimension greater than 2, this one any dimension greater than 3, this one is any dimension greater than 4. And when we do exactly the same game, but with constant mu, but not necessarily equal to 1, the resulting action is again a linear combination of this density that are conformally invariant in other dimensions. The only dimension that is keep on is 5 dimension, but then you have this, of course, it's a continuous, because mu is not necessarily an integer. And in this case, we can reproduce exactly the same. We have a metric solution that is given by this expression. The metric is not asymptotically too flat because of this. Of course, it's only flat when mu is 1. Okay, it's asymptotically flat. It has not the standard fall-off of Newtonian because of this mu. Of course, only for mu equal 1, we have the standard fall-off. And also, as in the mu equal 1 case, this extension to Weidia-like is exactly the same. I have this stress tensor that is like a pure radiation field that depend on the derivative of the mass. Okay, I think I'm good with time. So I'm going to give my conclusion. So what we have shown that for quite general Horndeski theory with arbitrary phi-dependent potential and without any apparent symmetry, we have shown that the model may admit interesting and explicit black hole solution. But it was very surprising for us that the resulting actions turns out to have a conformal origin, that it was non-Noetherian in 4 and Noetherian in 5 dimensions. Even if we never required that, you know, it was done by asking that the equation can be fully integrated. And it would be nice to understand the origin of this conformal symmetry. We have obtained linear and quadratic black hole solution, and both of them can be to generalize Weidia-like configuration by promoting the mass parameter to a function of the time, the retarded time. And we have completely specified the solution for a constant factor of proportionality, okay? But there is a question, what is going for mu that is non-constant? For example, the BBMB solution corresponds to a mu that is non-constant, so it's still an open problem, okay? Okay, I think I have finished in time. I thank you a lot for your attention.
Thank you. Are there any questions? Can you maybe explain, I don't know, a simple thing? So when you discuss uniqueness or non-uniqueness of the solutions, to my understanding, once you have the differential equations, you know what's the order of the differential equation, you know how much of boundary data you need to specify a solution, right? So it's kind of a well-known thing. Probably you impose something extra, like the way how the solution should behave at infinity, right?
Yeah, of course. You always require that it's asymptotically, that it's always asymptotically flat and things like that, of course. Otherwise, you will not have. Of course. I never mentioned explicitly, but of course you have to put boundary condition and things like that to specify exactly the uniqueness. Yeah, for sure. And of course, modulo diffeomorphism. That you can always make a diffeomorphism. No, yeah, of course. These are up to the boundary condition that you are fixing.
And what about numerics? Do you do numerics?
No, I never do, and no. To be honest, I have no idea about numerics for this. I know that people, for example, in the case of potential, they have shown, but I'm not sure about. For example, for this this uniqueness theorem that I was saying that it was open problem. I know that there is some results, but to be honest, the numerical result that they prove the uniqueness of this solution. But to be honest, I'm not sure about the pertinence of the result because of my ignorance. Huh? But of course, there are people that they are interested in showing this uniqueness numerically, because analytically is impossible.
I have a related question. So if I take some other model, not one of yours, but something similar, but I'll try to find a non-trivial solution numerically for the non-trivial in the sense that field phi will not be equal to 0. So but the model will be generic, like without any relations between parameters, etc. So will I find one in this region of parameters where the uniqueness theorem was not proved? No have theorem. So do you feel that at any parameters, like solution?
You mean, for example, let me try to understand what you mean. For example, in this range that is not covered by the scalar R, if I make numeric, probably, yeah.
So are there solutions there?
You mean numerically?
Yeah.
No, I don't know. I don't think so. No.
So you have to choose a very special model to have solutions.
Yeah, for sure. Yeah.
Not just analytical, even numerical solutions.
Yeah. Even in this case,
okay.
Yeah.
In your model, you assume that lambda is positive?
In this case, it was because the solution exists provided that lambda is positive to ensure that you have an horizon.
Not in this case. In your model,
sorry.
Gauss-Bonnet term.
No, the sign of lambda, it can be positive or negative. It's not playing any. I mean, here it can be both, positive or negative. There is no restriction.
Okay, thank you.
Any other questions? Okay, it seems that we don't have any further questions. So thank you very much.
No, thank you to you, and okay, thanks a lot for the invitation. It was very nice. Okay.
Thank you. Thank you everyone for coming.
Thank you. Ciao, ciao.